Hello, thank you for this virtual opportunity to discuss a concept that we have for the depositional character of lunar ice, and I hope you enjoy this presentation. This is part of the AAPG's Energy Minerals Division Astrogeology Committee, and I'm very happy that we have such a committee in AAPG because it's very important that we use our geoscience skills to help develop the future human presence on the moon and ultimately Mars. Lunar deposition by sediment fluid interaction is just not something we've been trained to think about on the moon. We talk about ejecta blankets and solar wind impacts and scattering and even volcanic influences and some vertical tectonic influences, but it's not something we're trained to really think about, a sediment fluid interaction. But now on Mars, deposition by sediment fluid interaction is commonly known. New examples are found almost every day, and the number of papers in the literature is increasing rapidly. This paper discusses the possible turbulent and instantaneous deposition of sediment fluid interactions when an icy comet impacts the lunar surface. And then the results of that are a depositional pattern that I'm going to propose and call tumultuites. The last humans on the moon were 1972, Gene Cernan and Jack Schmitt. Jack Schmitt, of course, was a geologist. But there's been continual exploration of the moon that you can read here. We have had 22 successful landers, not including the 6 Apollo missions. And although there have been some failures recently, last year, the Israeli Bereshit, the Indian Vikram lander, there are still 8 current active lunar orbiters and the current Chandrayaan rover. And we have seen physical surface samples from several places on the moon with data from actual lunar samples from the 6 Apollo missions and the 1 Russian Lunar mission. The future is bright for lunar exploration. 24 scheduled missions in the next 4 years. I don't expect you to read this chart, but all the red dots are part of the U.S. Artemis program. And all the blue dots are various landers and orbiters that are designed to look for additional ice and water on the moon. I show a picture of the Viper rover. The Viper rover is scheduled for launch in a couple of years. I'm very proud that some of my people are working on the instrumentation for this. But we're going back to the moon, and it's going to be a very active expedition. Continuing our basic lunar geology discussion relative to deposition, there have been numerous probes since the 1990s with instrumentation for surface mapping and geological and geophysical surveying. There is much data out there. To me, thinking about the lunar surface as an igneous provenance desert regolith, ranging from very fine-grained silt to scattered rocky outcrops, helps me mentally consider my depositional thoughts when I discuss the moon, and the fact that there are no significant organic compounds on the solar exposed lunar surface due to solar wind, cosmic radiation, and temperature. But understanding that the lunar surface is full of valuable minerals, some that you see here, including some rare earth elements. All of these minerals are oxidized forms, and so there's abundant oxygen on the surface of the moon as well, plus helium. Well, geotechnically, we have some data from these sediments, and if you want to study the physical properties of the sediments and the lunar surface that we brought back from the moon, look in the lunar source book. The references here. It's wonderful information, but we have particle size distribution, particle shapes, the gravity, density, porosity, compressibility, bearing capacity, all kinds of information on these sediments, plus some interesting information that helps us think about a depositional process. Lunar sediments are typically graded as silty sand or sandy silt, and typically described as well graded. We have drilled on the moon some, not very deep, a meter or two, and we have density profiles of the sediments, okay? And the density increases, and from the data we have so far becomes asymptotic
at about 1.92 grams per cubic centimeter. Okay, but the porosity of these sediments is very high, between 30 to 50%.
People had speculated about ice on the moon since the 1960s. And this continued through the 1980s, but data was sparse earlier and generally sparse later. However, in 1996, the Clementine spacecraft detected the possible signature of ice on the surface of the moon. This really got people excited. Then the Lunar Prospector in 1998 had a neutron spectrometer experiment on board that could detect very minute amounts of water ice by looking for thermal neutrons, and it detected water over both the north and south polar region at significant percentages. What's important is this neutron spectrometer could not only look at the surface of the moon, but to a depth of about half a meter. So we were beginning to see ice on the surface and below in the subsurface. Then an experiment in 2009 later was the L-Cross and Centaur experiment, where they crashed the Centaur stage into the Cabeus crater and looked at the plume, and they detected hydroxyl at roughly 6% water and some nearly pure ice crystals. And then Chandrayaan-1 in 2009 continued to find hydroxyl signatures. People were really beginning to believe the probability and the existence of water on the moon. The 2009 discoveries of water as being a probability, of ice as being a probability, was a game changer. That means that we now have a source of material potentially for propellants, drinking water, processing water, manufacturing water, maybe even some other organics in the ice. It also added a concept to the discussion of lunar deposition, where we're not just looking for impact effects and debris scatter and moonquakes and things like that. We're now looking at potentially lunar ice freeze thaw at the ridges and edges of some of these cold traps. It's often been said that to study the moon, you need geochemistry and geophysics. That's still true, but we also need other geological concepts like the four-dimensional geologic depositional character, an understanding of that, of these ice deposits for economical, effective, and sustainable utilization. As a result of teleworking and isolation due to the COVID pandemic, I began to catch up on a lot of the literature that I had been remiss upon reading. And the image at the right is from the Lunar and Planetary Institute and the excellent work done by Stoper and Meyer and their associates. And this is the lunar South Pole. The crosshairs are in the pole, and the dark areas are craters with permanent cold traps. Cold traps exist because the angle of the sun, the direction of the solar wind, inclination of the lunar poles, and the topography all creates areas that are permanently dark, permanently cold, with excellent potential for long-term survival and existence of lunar ice. So these areas are of great interest, particularly in the U.S. Artemis program. You see the craters Shackleton, Cabeus, Shoemaker, Amundsen, Hayworth. These are all prominent cold traps that are of great scientific interest. Right at the crosshair is the Shackleton crater. It looks smaller than the others, but it is 21 kilometers in diameter and 4.2 kilometers deep, just to give you an idea of the scale.
Well, zooming in a little bit using other Lunar and Planetary Institute data, you can see that the Shackleton crater is on the image on the left. You can see the Shackleton crater. You can see the crosshairs designated where the pole is. There's a box around the Shackleton crater, and the image on the right is from Zuber et al. And is a very large or higher scale look at the interior of the Shackleton crater. This fascinated me. And I actually pulled this image up and made it the background on my big screen associated with my computer. And so I could sit there and look and think about this quite often. This is elevation. So we're seeing topography on the interior of this crater. And as a geologist, every geologist seeing this video immediately starts to put patterns to what they see in this figure. So did I. And I began to think, okay, we're in a cold trap. We've got measurable satellite signature that suggests hydroxyl radicals and ice in this crater. What could these patterns actually mean? Are they just sediment? Are they sediment and ice? I had several questions to ask. So I started drawing on it just like any geologist would. You could put thousands of lines on this image to come up with various patterns. And I studied some other resources about water vaporization with comets in general. Greater than 99% of the water that's associated with a comet, the ice, is vaporized when it impacts. Almost all models show that, but not all of it is. Just for my mental research, I assumed 1% remained. And if that happens, I believe there may be an instantaneous deposition as the ice comet mass interacts with the excavated lunar regolith from the impact. And then you get immediate particle and density sorting and even some geochemical interaction on large and small scales. Can this concept be tested? Is it possible to predict based on existing geological concepts? I believe so. Okay, and here's my initial concept. And I apologize to all my friends that do very advanced four-dimensional modeling. This is very simple, but it shows my ideas. You have an impact, the impact and the comet break up. You start to break up the regolith. Most of the water in the comet's volatilized away. But at some point in that process, some of that remnant ice starts to interact with that disturbed regolith. And it becomes very turbulent, instantaneously turbulent, and massively turbulent. And pulling that time 3 period over onto this slide, I believe that the result of that looks something like what you see in red here, tumultuate emplacement, in just a few minutes, if not a few seconds. Okay, and so you would have distributed that, like that little red figure on the bottom right. You have distributed ice, probably from fallout, but you also have tumultuously deposited ice from the impact, mixed with the sediment in various tumultuous shape forms. They can be bedded, they can be circular, they can be ball shaped, they can be various structures depending on the turbulent process at the time. And this, I believe these exist. I believe you can predict where they would be located. And I believe it's going to be possible to predict even what the form of these are to help you go after the ice in whatever shape or form it might be within these bed forms. And I call those tumultuites. And so I did a quick experiment. You know, I teach geology a lot online, and I had a lot of equipment with me as we were doing this teleworking, and derive some observational assumptions that I wanted to see or believe would happen, assuming some additional conditions that you can read here. And then I developed a hypothesis that a direct or glancing impact from an icy comet will create a crater, where as a result of the mechanics and process of impact, ice will interact with sediment, causing the ice to survive and form an observable and predictable depositional package. And I created an experimental concept to do this, which we'll see in the next slide or two. Picture on the right shows my experimental setup. Basically, I created a simulated lunar regolith. I did it with very fine grained sand and bentonite. And we do have lunar simulant that we use in our research programs, but it's considered a hazardous substance, and we weren't on site to get it. I wasn't on site to borrow some. So I created my own. And you can see from the grains on the center figure about the size of my lunar simulant. It was very fine grained sand to silt size, which I think. This image shows you some of the impacts as they happened. I used lead shot as a test case to see if the concept was going to work. And then I used ice ovaloids, little ice balls, as my comet. One thing we discovered was that the ice balls were much harder to aim, so I was using a slingshot as an impulse source, and you could see the velocities we obtained in the previous slide. But I had to move my impulse source closer, within half a meter, to make sure I could aim the comet I was trying to cause the impact. And this worked very well as just a very simple experiment. And you can see the results here. Okay. Most importantly, we did meet some of the scaling criteria necessary for these experiments, in that we did hit the approximate 5 or 6 to 1 diameter to depth ratio that is in the literature. Plus, we had some of the exact same geomorphic features that are found in the literature. The picture on the top with the PB is a remnant lead shot. That would be like a stony meteorite hit, and you immediately recognize that pattern. The pattern on the bottom is an icy hit, and they were almost always a little bit geomorphically different. Okay, and it was this that got me thinking about this concept of the tumultuites, and that it might have some truth there. So, expanded a little bit. Here's a lead impact crater on the left and an ice ovoid impact crater on the right. And you can immediately see, just from the image alone, that there are 3 distinct areas where the particle size has been sorted by the impact. I went to great trouble to fully homogenize this lunar simulant that I was using after every impact. So after every impact with ice ovoids, I got this sorting pattern. Pattern varied by impact, but it was always this 1, 2, 3 pattern that looked like this. Okay, and I was thankful that the bentonite actually held the shape of the fluid transfer to my lunar simulant for just a little bit, a few minutes, and then it would eventually dry out and these shapes would fall apart. But they were, I could photograph them, I could use my digital microscope and figure out the grain size distribution within them. But it's this is a depositional pattern, okay? And this depositional pattern has conditions to it. It has descriptive conditions to it. But also, if you look closely, you see this turbulent motion within these bed forms. Those are areas where the bentonite has separated itself out to form lenticular, circular, or spherical shapes based on the impact, and contain more moisture, more water than the sandy particles. So, is this tumultuous deposition? I believe it might be, and that might be a very small example of a tumultuite. So, in summary, volatiles and water is the major goal on the moon. We presented a conceptual model for ice emplacement from turbulent mixing based on a comet impact with lunar regolith, and we termed these formations, these depositional patterns, tumultuites in this presentation. And then we did a very simple experiment to see if there was any validity to it. It looks like there might be, but I would really like people to do more advanced research into this with a more robust process and see if these tumultuites might be something that is useful for our exploitation of ice on the moon. Some of the key references I used are here. This is not exhaustive, but it's fairly comprehensive. If they're here for you to use.
Thank you for this opportunity and for listening and considering. And if you would like to contact me with any questions, please do so.